Welcome everybody on Zoom. Welcome everybody in the lecture hall. So we are going to start and continue what we were doing in the data modeling section today. If we have time, we might even start processing data with MapReduce. But before that, we need to finish, the validation of the data. As a refresher, the reason why we are doing that is performance. Because if you don't validate data and you just directly read textual JSON or XML from a data lake, this is going to be very slow. When you validate data, you identify a structure in the data. You notice that there is always the same field, that it's always an integer and so on. And then you can start compressing the data. For example, in order to store an integer, you don't need to store every digit. Instead, you need to store, for example, the 32-bit version of it. So by compressing data, you save space. It means that you fit much more on a single machine. Perhaps you don't even need the cloud. You can do it on your laptop. The second thing is that since you saved space and you fit more in less, you read also the data faster. So the number of bytes per second that you read is limited. But if you compress the data, the amount of information you read per second is much higher. And that means a much faster query. That can be the difference between a query that takes 1 hour and a query that takes 30 seconds. This is how important validation is. Now in SQL and relational databases, you get it anyway because you have to specify a schema, but not in data lakes, because for example, if you write down data as a log, you just throw the data into a file by appending to the log, right? So this is how you don't need a schema for that. All right, for whom is that clear that we need validation? All right, and in the exercise, we'll actually show you how to do that. We'll give you a data set in JSON, and we'll show you how you can validate it and convert it to a binary format, Parquet, and you can see the size that will be much smaller and the query will be much faster. Okay, so I have 2 questions for you in order to start. So I'll start with one. So let me go with this one. You might not know yet. I don't think that I showed that to you, but you can try to guess what this is. D1DT7H2EMS3S. Is it a UTF-8-based encoding of a protocol buffer? Is it a string in the lexical space of datetime duration, which is an XML schema type? Is it an instance of a BSON instance in base 64, which is a binary encoding for JSON? Or is it the name of a new robot in Star Wars? The answers are coming in. Let's look at your answers. We have Star Wars fans, or maybe they know things I don't know on the next movie that's going to appear. And we have a majority, and it turns out that the majority is, drum roll, correct. So you know that in XML and JSON, it's text. So no matter what you say, we will see we already saw actually that there's plenty of types that you can have. You need to be able to express it in text as a string. This is a duration. It is 1 day, 7 hours, 2 minutes, and 3 seconds. This is what it is. The letters P and T are here in order to basically identify the literal, right? It starts with a P, and the T is the same separator that you have in dates and date times, that you have a T in the middle, right? All right, so this is what it is. It's just a duration. And by the way, you have it also in the JSON types that we will look at. So it's not just XML, this also applies to JSON because it's a string, so it's not tied to any particular syntax. It's just a literal. Okay, let me also ask you this. You don't need to actually know what we will do today because we haven't done this with XML yet, but I think you can still answer this question. I'm giving you a document and I'm asking you, is it well-formed? Is it valid? Is it both or is it neither? Right, the answers are coming in. Let's start looking at the statistics. Aha, we have two competing answers. Be careful, the majority is not always correct, but it sometimes is. Last chance to change your answer. 42, that's a great number to stop with. Oh, 44, okay. So it is well-formed only. Can anybody tell me why it's not valid? Maybe the cube. Oh, that's far away. Ah, oh. Okay.
So my guess, I really don't know, but my guess would be that since we don't have a schema that we validate against, it can't really be valid.
That is correct.
Yeah.
There is no schema, so you cannot make any statement about validity. Yeah, you're absolutely correct. Validation can only be done if you have a schema. And I'll show you what these schemas look like very shortly. Well-formedness is a yes, no, you don't need a schema. Either it's well-formed or not. It's basically, do you follow the rules of JSON or XML? But validation, you need a schema. And this is the reason why this document is only well-formed, because I didn't give you any schema. I could make up one, right? Make up a schema, but since we don't have any, it's not valid. Okay. Now, let me switch back. How do I do that? Yes, do share. Maybe speak in the microphone while I switch over. Yes.
Can you define a schema for the previous XML?
Yes, I can. Yeah, okay. We could. You can absolutely, actually, whatever XML file I give you, I think you can always define a schema, always. Whether that schema makes sense or is useful is another question, right? But I think you can always define one. The only problem is that if the XML file is a huge mess, you might actually get a trivial schema that just says allow everything. That's the only thing you need to be aware of. The real cases where you actually do define a schema is if the document has some structure that you recognize and that you want to capture with the schema.
Like you can always define a schema for JSON or XML, like no matter how messy.
Yes, exactly. It's just that if it's messy, the schema will be trivial. It will not be, yeah. And if the schema is too trivial, you will not be able to convert it to an efficient binary form, right? So I will tell you everything about that, the conditions that you need to fulfill in order to be able to optimize with a binary form. But the schemas are so general that they go beyond that. Okay. All right. So where are we? Last time we finished on the types, and so I threw this at you, which is a list of types, and this is actually very general. I told you this is fully technology independent. Now you can look at any technology and look at the types in there. It's almost guaranteed it will be more or less the same. Then how you call them might change, and the ones that are there and that are not there might change, but it's the same, really the same idea everywhere. So it's very important that you develop this generic and neutral understanding of type systems so that you can then adapt to absolutely any language. What we will focus on, but it's just for the purpose of this lecture, is the first and third column, but probably notice it's actually the same thing, which are the standard W3C types defined for XML schema, and they are the same in the JSON syntax that we will see, because this is actually not even depending on XML in any way. This is sufficiently generic. All right, but now we start validating data, and I will show you what schemas look like. I'll start with JSON. JSON was actually homemade in the sense that we developed it with a few colleagues, and my motivation for it was teaching. It just makes the schema the schema language so simple that it's very intuitive, and I hope you will find it intuitive. Then I'll go to JSON schema, which is more complex, but you will see that once you have seen how JSON works, you will probably see that it's the same patterns all over the place. And then XML schema, which scares a lot of people, but you will see, hopefully, that it's just, again, the same all over again. It's always the same ideas. So after that, you should be able to quickly learn any schema language, and you will just know the general concepts, and you just look up the documentation for the details. Okay, so when we validate, we'll always need two things. We'll need a document and we'll need a schema, right? So the document is called the instance, and the schema is where we specify the structure that it has. So this is where we left last time. The document is on the top. This is the actual data that we want to validate. It will always be well formed, but now we want to validate it. And at the bottom, you have the schema. So here what happens is, in the schema, we say that we want a key called last, and we would like the value associated with it to be a string. So is this valid? The answer is yes. We have a key last, and this here is a string. So this is fine, right? So here it's a yes. This is valid against that schema. And you paid attention, I said valid against that schema. If I change the schema, it might not be valid against a different schema. Against this one, this instance is valid. Okay, let's make it more complicated, but you see how intuitive this is, right? The schema basically looks very similar to the actual document that you're validating. So here we say last must be a string, first must be a string, last is a string, first is a string. Yes, that's valid, right? Next, you need to know that if I specify here a specific key with a type, it's still optional. If it's there, it must be a string, but if it's not there, that's fine too. Right, so it's optional. So here I don't have this first here, but this is okay. This is also valid. Right. In fact, everything I'm showing to you here is valid. If there is a counter example, I'll tell you, but this is all valid. Okay, who is following? Okay, who finds this syntax easy? Okay, that's the goal. Okay, now how about requiring it? Because if you have a schema and you want schema validation, maybe you want a field to be present. You don't want the documents missing that field to be valid, right? This is what you do with an exclamation mark at the beginning. This is actually the compact version of the schema. It's meant to be compact. So with an exclamation mark there, you make it required, right? So here, this is valid. If I didn't have this, this would be invalid because I'm requiring the field first. These concepts that I'm showing you here, I'm using JSON, but almost any schema language allows you to do that sort of things, right? I will show you the same in JSON schema, in XML, how it's done, but you need to focus on the general concepts and the features of the schema. Okay, so we can require fields, or we can make them optional. Then we can have other types, right? I took the example of string, but here this is an example with an integer, right? So this is integer, and here 142, so this is valid. In fact, you need to be aware when you validate, and this is also the logic in XML, that in the case of JSONs, you only look at the literal. Here, this is really at the raw level, this is text. This is just text with the string 142, even if it's not quoted. So the question that you ask is, this lexical value, this sequence of characters, is it in the lexical space of integer? Well, 142 is in the lexical space of integer because you can actually parse that as an integer. If you try to parse it, you succeed. If you tried to say last integer, this would fail because this cannot be parsed as an integer, right? Whether or not it's quoted is irrelevant for validation. Even if it had quotes, it could still be successfully validated against the type integer. And then in memory, you would save it efficiently with some optimized format that captures integers. All right. Booleans, it's easy too. You say physicist Boolean here. That's again the type, true. All right. And in fact, what you can put in there is anything from the whole list that I showed you before, right? Everything you have here, you can put as a type, right? Okay. So getting back, Boolean. And you also have a type null that just contains the value null. So if you really want to ensure that a field is null, you can just put null in there. There are also ways to do union between integer and null. So you can say it's an integer or it can be null. This is also possible. In fact, this is done with adding a question mark. I just don't have any slides. Okay. Now, more complicated. What if we have nestedness that we want to capture? So, for example, I might have location here, which is an array there with Switzerland and US. If I want to be super generic, I can just put item in there. Item is the super type of everything. Everything is an item, right? So if you put item, it accepts anything, and in particular, it will accept an array. Or, so this is another example, right? Where you have here an array of items. So this is the syntax to say it's an array of whatever, and that whatever is item. So this is an item, this is an item, this is an item, this is an item, this is an item. So you can use these square brackets exactly as they appear in the original file. So you see, this is very visual. This is very visual, how it resembles the file. And if you want to be even more specific, you can say, I want an array of integers, right? This is an integer, this is an integer, this is an integer, this is an integer, this is an array of integers, and this is the syntax in JSON. Why couldn't I do it here? Because here it's a mess. This is a mess, right? This is just to show you an example of a mess. Why? Because you have plenty of things in there and they are just different types. So this is why here we were kind of forced when we built the schema to have the most general type in there, right? Who is following? Okay. Okay, so this is for arrays of integers. Now you see the logic, right? Because it nests. Now I can nest an object in an array in an object. And here what I'm saying is that I want an array field that is an array of objects, and every object, when it has the key foo, must be a Boolean. Is this valid? Yes. Array is an array of objects, and I have here a first object where the field foo is a Boolean, so that's good. And here another object where the field foo is a Boolean, so that's good too, right? So you see how the visual is very similar to the actual document that you validate. It's just that in the schema, you only have one single value in there in the array, which validates again every member that you see in the instance. Okay, who is still following? Who still finds this easy? Okay.
So there's one question.
Yep.
Every level of nesting here, fully full 14, is allowed to be empty?
Right here, can this be empty?
Yeah,
Is it the question?
So it's right. I'm not sure if I can understand the
Yep.
question. So, but
So let me ask a question and answer it, then you can tell me if that was your question.
Yeah.
If here you have a R that is an empty array, so you remove the two objects here and you just have square brackets, the empty array, is it valid? The answer is yes. This is an array of objects that can be 0, 1, or anything. So this would be also valid if the array were empty, right? Was it your question on Zoom, just to check that this was your intent?
Yeah.
Yeah, all right. So I guess I answered it. So there is no constraint here on the size. You can actually constrain the size. You can also say it has to be between 2 and 4, but you need to enter expert mode for that, right? So I will talk about expert mode a bit later, but there is an expert mode in which you can also make constraints, and you can say, I want at least 1, I want at most 10, or I don't want to limit at all. But in the compact syntax, this easy syntax, there is no restriction on the number of members, can be 0, can be 1, can be 10, anything. Okay. Now, the next thing that I want to showcase to you as a feature of many schema languages is the ability to close or open the objects. What that means is here, I have last and first as keys in my schema. Do I allow more fields? What if in my instance, I have dynamically plenty of more fields? Well, here it's forbidden by default. If I try to have new fields in the instance that are not in the schema, that will not be valid. Okay, but we can change this behavior. It's a flag. You can say accept additional fields, right? So this is called an open object type. By default, it's a closed object types that really wants exactly these fields to be in there and nothing else. An open object type will allow. However, we need to enter expert mode. So don't be scared. We will enter now expert mode. It's exactly the same. You see, there is one here. There is an expert mode in that screen. I can switch to basis mode. This is not too scary. And expert mode, I have plenty of tabs that appear all over the place, right? So you know that. So let's enter expert mode. So expert mode will be slightly more verbose. This is the alternate syntax that looks like this. Don't be scared. It's just an expert mode, right? So as you can see, it says the same thing, but it's just more verbose. So we say the kind is an object, the base type is object, directly derived from the topmost object type. And the content, which here is an array of all the field descriptors. So the first field descriptor says the name of the field must be last and its type must be string. And the second field descriptor says we have a field whose name is first and whose type is string. This and this is the same thing. This is just the basis, the compact syntax, and this is the same thing in the expert mode. Okay, I hope I didn't scare you too much, because this is extremely powerful, because if you enter expert mode, then you have plenty more bells and whistles that you can configure that wouldn't be available in the compact syntax. And in particular, if you switch to expert mode, you get this additional thing that you can configure here, which is closed. By default, it's true. So it's a closed object type and it wouldn't allow extra fields. But if I say closed false, then it's no longer closed. And now I can add this year 1905, which is nowhere to be found in the schema. But this is fine because we said it's not closed. Okay, for whom is that clear? Okay. And there's many more features I will not show you, but there are many more features in there.
Yep.
Do we have a question?
Yeah, there's one question. What's the difference between kind and base type?
Ah, okay. So this is the expert mode thing. Then let's explain expert things then. Kind is just, is it an object? Is it an array? Is it an atomic? Or is it a union type? There's only these four kinds, nothing else. Base type is in order to do a type hierarchy. In fact, I'm pretty sure you already are aware of how this works if you program with Java or C++ or Python and you do object-oriented programming, right? You can have a class that is a superclass of another class that's called the subclass, right? So you can call it superclass subclass, or you can call it base class derived class, right? Base type, derived type. This is exactly what it is. Basically, what you can do, it's not part of the material, but just so you know that it's there, I can define a type here. I could give it a name, right? My type, or maybe person, let's call it person. Then I could define another type that has kind object, base type person. And then I can start adding new fields. I can start restricting the values of the fields and so on and so on. So I can build a whole type hierarchy of objects, of arrays, of atomics, and so on. But if you don't use that hierarchy and don't derive from anything and are just on the top level, then the base type will also be object, because object is the name of the top uppermost type for objects. Right? Did I answer your question on Zoom? Yeah. Okay, awesome. And we have questions in the room too. Maybe you can throw the. Yeah, awesome.
Out of curiosity, if we have an overlap with a field that's called kind, what happens?
Oh, it cannot happen. And this is actually a good opportunity for me to explain to you some design things in that type of things. You need to understand that when you design the layout of objects, you have a static approach and a dynamic approach. The difference between the two is whether you create new fields on the fly or whether you stick to fields that must always be the same. If you look at the compact syntax is dynamic, because here you can put any fields you want. It's whatever fields you want to validate against, right? So last and string and first can be replaced with anything you want. This is dynamic layout design, dynamic. Here, this is static layout design. Why is that static? Because all of the keys you see in there, kind, base type, content, name, type, they are predefined and specified in the JSON specification. This is static. In the expert mode syntax, you will never ever find any other keys than the keys that are specifically designed in the specification. This is why you cannot ever have a collision. Because if you want to define a field to validate that would be called kind, then kind wouldn't collide with this right here. There would be no collision because kind as a field that goes there would go as a value, not a key, as a value associated with name. Does it make sense? This is why it never collides. And the fact that you want to avoid collisions, so the question that you asked is exactly the motivation why, when you can, static layouts are very, very good. With static layouts, there are no surprises. With static layouts, you can compress to parquet and make it safe space. And on top of that, with static design, you can do many more query optimizations that you couldn't do with dynamic design. Nevertheless, in SQL, dynamic design is absolutely possible. So you can both do it statically or dynamically, meaning the keys can be known in advance or the keys can just be discovered on the fly when you read the data, right? This is a super important topic. So thank you for asking the question and giving me the opportunity to explain that. So as you can see, the expert mode is a static layout type because you only ever get the keys that are specified in advance, while the compact syntax is a dynamic design. But the whole point of that is to resemble the instance, right? To look visually like the instance. So this is why it's dynamic. Who understands the difference, static, dynamic? Okay. And again, if you have to associate with something in your mind, static means better performance. You can optimize more, you can optimize the space on the disk more, but I'll come back to that with the data frames later. Okay, so now in expert mode, so you can close and so on. There are many, many, many more things you can do in expert mode, but I just didn't want to throw them at you. I can give a link, of course, if anybody is interested. So is there another question?
Yeah, there's another questions. Can we make the schema even more restrictive by allowing strings of certain format?
Yeah.
For example, with using regex.
Yeah, you can, absolutely. There is, in expert mode, you need expert mode for that, but in expert mode, you can say the string must have exactly the length of 3, or it must satisfy this regular expression and so on. You can absolutely do that. And these are features that many schema languages have, right? You can do the same in JSON schema, you can do the same in XML schema. This is absolutely possible. So you can, in fact, this is called defining your own types, because what you're doing, in fact, when you say that, is that you define your own type, right? For example, a shoe size type, right? Okay, so this is just a recap of the features that we have in a schema language. And this is not just for JSON. This actually applies to many, many schema languages, but just to give you an idea of what we find in schemas, you can restrict values to a specific type. For example, you can say, I only want to see integers in that array. Or I can say, that field must always be a Boolean. So you can restrict things. If you don't want to restrict, you can too. You can say, okay, this is just an item. It's an array of items, and I don't restrict. So you have the control of that. Second, implicit cast. What do I mean here? This is when I said, when you parse it in memory and you validate, I told you that you don't just validate, you annotate too. Remember, validation, annotation. This is something that goes hand in hand. When you validate and you have the answer, yes, that's valid, you will also take the opportunity to convert everything in memory to the actual types that you just validated against. So if you read in the data lake, in the text 2134 that you tried to validate against an integer, then the answer is yes, that's valid. That is actually a literal that can be interpreted as an integer. But this 2134 that you see on the right, which is the implicit cast, so you cast it to the type that you validated against, in memory, it will not be stored as 4 bytes, 2134. It will be stored as the actual int, for example, int long or whatever you want, so a more efficient format. So you save space, plus then you can compute. You can put them in the CPU registers and start doing arithmetics and so on. You couldn't do that with the text, with the literal. Okay, so this is the cast. This is when you annotate the actual memory representation of the data. Then you can require a value. Remember with the question, the exclamation mark. So you can say you want foo, the field foo, to be there. Or you can say, I don't care if it's there or not. I'm fine, it's optional. So you can require or make optional in your schema. The next thing you can do is what I explained as open and closed object types. So you can say, I only ever want exactly the fields that I have in my schema. I can even make them optional or required, but I don't allow anything else. Or you can say, I am open to any other keys that there can be dynamically. Of course, when you have open objects, this is dynamic. It's not static. If you have a closed object types, you have static layouts because the keys are all in the schema. If you have an open object types, then this is dynamic because then you can have any keys you want and you don't know in advance, you will just discover them when you read the data. Okay. What you also have that I didn't show you, but you can, is in the schema, you can also specify default values. For example, you can say if you have a field foo that is a Boolean, but you don't find it in the data, it's optional, so you just validate anyway. But in the memory representation, you can specify a default value to be automatically added in memory. If it wasn't there, you just add it. And when you query the data, you will actually see that default value instead of being missing. Okay? This is another feature that you also have in plenty of schema languages. And many schema languages also give you support for primary keys. What do I mean with that? Imagine you have an array of objects. Maybe you would like these objects to be uniquely identified with some key. For example, you would like the values of foo to be unique within the array. This, for example, would break the whole thing because here you have 1, 2, 3, they are unique, but 2 is repeated twice. So you could not have foo as a primary key. But in a schema, you can require that foo is a primary key within the objects in the array, right? For whom does that make sense? All right, so this is the sort of things you can do with a schema. Now, just to give you an example, this is the great language game, so we'll use it as a data set many times in the lecture. It's, I think, millions of that. We have millions of objects like that that correspond to people playing, trying to recognize languages. On the top, you have one of them. There's millions of that, but I'm just showing one. And below is the schema. And hopefully you will see that it's very visual, right? So there is a required field guess of type string. There is a required target of type string. There is a required country of type string. You could even define a subtype that restrict the length to 2 if you want it. We didn't do it here. Then we have a required field choices that is an array. You see the square bracket, an array of strings. Yes, that is an array of strings. There's 4 of them here. You could also restrict to be exactly 4 because actually in that data set, it's always 4. So you could go to expert mode and then say that it must be 4 of them. Then we have sample that is hex binary. Hex binary is yet another type. What is it? It's just a base 16 encoding of some zeros and ones, right? So this is just base 16. You can validate that as hex binary. It exists. And here, this is a date literal, dash separated, year, month, day, right? So you can say you have a date here. For whom is that clear and intuitive? Okay. Here's another one. Remember this tidy document that I showed you last week? This is an example of document. When you see that, if I did my job well in that course, it should itch you to validate it. You see that you want to rush into validating it, right? So this is how you do it, right? This is the validation, the validated procedure. You do this schema, a required A that is an integer, yes, A is 1. Required B that is a Boolean, yes, and C is an array of objects. What are these objects? A required field foo that is a string, yes, that's a string 3 times, but bar we cannot require, it's missing there. So no question mark in there, just optional. And that's an array of longs. Is it an array of long? Yes, that's an array that will validate against long. Okay, so this is another example. So here again, the goal is that it's very visual and intuitive to design. Okay, you can play online if you want. There is this address here. We have a public machine. Just be nice with it because it's just 1 gigabyte of memory and 1 core. We have a few instances in the cloud. So if you crash it, then you need to wait until it's restarted. But it restarts everything every day in case it crashes. But you can go to that page here and you can put an instance on the left, a schema on the right. You can even go to export mode if you want and try out the verbose syntax. Okay, so this is for you to play with as much as you want. Okay. Good. So that's our first language, our first schema language, which is JSON. Now I'm going to go into a second one. This one is actually nowadays very popular. It's a bit more complex because it was done a bit earlier, so it didn't inherit many things that were actually takeaways from XML schema. But as a matter of fact, this is what people use today. So I'm going to show it to you. So this is a simple scenario with JSON schema, so it's a different language. We want to validate last Einstein. So here we say type object, and the properties are last, which is a field of type string. Now you can already see that from a modeling design, it is a little bit because it's not quite static and not quite dynamic, right? Because you could see, okay, it's static because you have type, you have properties, and you have type. These are always the same. But it's also dynamic because in properties, you have the keys that basically match the instance. So it's kind of a hybrid thing between dynamic and static, right? But that's how it is, all right? So last is of type string. Then you can add more properties in there. First of type string, you see. You can decide if it's optional and required. So like JSON, if you don't say anything, then it's optional by default, right? So if first doesn't appear in the instance, then that's fine, it's optional. How do I require fields? I do it with an extra field in the schema that's called required. That's also a static key, so it's known in advance, always called that way, required. That's an array of string, and it's just the list of keys that you want to require. So here you say name and first must appear in my instance. So that's the equivalent of the exclamation mark in the JSON compact syntax. We still following? Okay. So hopefully, now that we've done it with JSON in an intuitive way, that should seem easy because we are just looking at another language, but it really does the same thing. Yes?
This is just for sanity check. Name should actually be last, right?
Correct. Yep, correct. That's a very good catch. Can you make a note, Fabio, for me to fix it? Yep. Thank you for catching this. Yes?
I'm wondering, how is this different from the expert mode that we mentioned before?
Oh, this is there's only an expert mode there. There is no, the JSON schema only exists with this syntax. It is actually related to the expert mode, meaning that if you look at this and look at this one, there are commonalities, right? It resembles it. The difference between the two is that this export mode right there is strictly static, which is good design. Basically, it's strictly static because all the keys will be anticipated in advance. There are other differences that I will tell you on the fly, right? So but in principle, this is very similar. But there is a reason why it's very similar, is that all schema languages will in fact be similar, right? If you find other schema languages, it's very likely it's going to look something like that.
Okay, thank you.
Okay. Yes, another question over there.
But why is expert mode strictly static if we can put closed equals to false, and then you can add keys on the fly?
It's meta. So what I call static is a design where all the keys are known in advance. When I was saying that the design is static, let me go back to the slide to be very precise on what I'm saying. What I'm saying is that the design of the schema language is static. In that case, the instance is dynamic because you have an open object type. So you could say the instance layout is dynamic. What I was saying when I meant that it's static, I was talking about, and here hold your breath, the schema against which this validates. Does it make sense? Because this is JSON. So you can also validate the schema against a schema. So you could call it a meta schema or a schema of schemas, right? So if you tried now to write a schema language, a schema document to validate the schema itself, that schema of schema would be here closed true, right? And this here, seen as an instance, would validate against a closed object type. Does it make sense?
Yes.
It's a lot to digest, right? Because it's meta. It's like again, this is inception, like the dream in a dream in a dream in a dream.
So this is static. I mean, the schema is static, but the instance is dynamic.
Exactly. So what I'm saying, let's forget about the schema of schemas. If you forget about validating the schema itself and you just look at the instance, what I'm saying is that if you have closed false, then you have a dynamic layout. If you have closed true, or if you don't save, which is by default closed true, then you have a static layout, right? This is what I'm saying. And what I was adding on top is that since it turns out that the schema itself is also a JSON document, then you can view this also as an instance. And then maybe it would be below at a third level, you can put a schema under which this is valid. And what I'm saying is that in the schema that would go down there to validate this, you would have closed true. Why? Because there's always kind, base type, content, name, type, closed. You will never see anything dynamic in there, in the schema itself. Right? Does it make sense? Right. Okay. Okay. Yes, another question.
Yeah, so I was wondering, in case of the instances of the actual JSON instance of the objects, it made sense to have the notion of static versus dynamic, because with static objects, we can do all sorts of optimizations.
Yes.
But in the case of the schema being itself static or dynamic, I am not sure I see the point in having this distinction.
Oh, so here, because performance is one aspect of the static design. Another aspect of a static design would be best practice. It's that it's cleaner, and if you want to implement the actual schema engine to do the validation, it's much simpler to implement a schema engine if you have a static layout in the schemas that you read. Right. In fact, the sort of things you can do when you have a static schema is that you can map them to Java classes. You could define a Java class in which you say in your Java class, you have a Java field kind that is a string, a Java field base type that is a string, a Java field content that is a list of maps, and so on, or a list of classes, and then you again have name that is a string and type that is a string, right? So here, it would be for ease of implementation of the validation engine. It's easier to implement the validation engine, but also because it makes learning the schema language easier. If I tell you this schema language is designed in such a way that there is a finite number of keys and it's always the same keys, then it's easier to learn because all you need to do is go through the keys and know what they do, right? So it's also a pedagogic. So there's many reasons basically for favoring a static design when you can. And here, the decision for the dynamic design was because we wanted to mimic the layout of the instance, right? And you can see that in JSON schema, they did something hybrid. So they basically said, okay, this is mostly static outside, so type properties and so on. But in the properties, they switch over. If you wanted to write a schema for that, this would be a closed object type. The properties object would be an open object type because you need here to allow keys that you can have anything you want here. Does it make sense? That's a lot to digest, right? Because that has to do with performance in the case of the instance. It has to do with best practices in the sense of the design of a JSON dialect itself. Right?
There's one question,
Yep.
follow-up question on Zoom. So the schema can only be static, which is validated by the second level schema, but the static dynamic instance is validated at the first level schema itself.
Can you repeat slower? I'll try to parse that.
So the schema can only be static, which is validated by the second level schema.
Yes,
I guess
we are
talk
talking about
this,
JSON here.
yeah, this one.
Yeah, we are talking about the export mode. Yes, this is static, and the second level schema would be a closed object type.
Yeah.
Yep.
But the static dynamic instance
Static
is validated.
dynamic.
Yeah, so let's talk about the
Oh,
example,
here,
right? The
this
instance.
here, the instance. Yeah.
Is validated at the first level schema itself.
And this is an open type, so this is dynamic.
Yep.
So this is
Okay.
correct. What you're saying is correct. Yeah. Yeah. So again, it's very meta because since the schema itself is JSON, you can go one level more and validate the schema itself. So this is why we have this additional level. But I think most people that validate data, they are not really aware of that extra level and of the meta aspects of validation. They actually don't care about the schema of schema. But if you're a geek like I am, then maybe you're interested in these things. It's like in theoretical computer science, like a program that writes itself or these kind of things, right? So you can have a schema of schemas, and then you have this second level. Yes, there is a question there.
But when we say static layout design, we mean that the schema is static, right?
Yes, I'm saying that the schema language is static because in the schema, it's always the same keys. This is what I'm saying.
Thank you.
Yeah. Okay. Basically, it's a bit, let's take another example. A company can have customers, right? You can go to Coop or Migros and buy stuff. You are the customer of Coop or Migros. So from your perspective, you are the customer and Coop or Migros is your supplier, right? It's the shop. But now take the perspective of Coop or Migros. It's a firm. They also have suppliers. Maybe they have SAP or I don't know, to manage their data. Then they are the customers and SAP is the supplier. So you can be both the supplier with respect to your customers, and you can be the customer with respect of your own supplier because it's a whole chain. This is the same here. We have the notion, just like customer and supplier, we have the notion of instance and schema. So in that case, the instance is here and the schema is there. But just like Migros and Coop can themselves be customer of somebody else, the schema can also be seen as an instance that is valid against yet another schema. Was it clear? Awesome. Yes, another question? Then we take a break because it's
so in that you go up the branch of suppliers. You get to
yes, this is where the analogy stops, because here you just stop when you have the schema of schemas.
But then, because apparently online that validates itself.
Yes, in fact, yes, that's a very good observation. This is like the program that writes itself. Indeed, it is true that the schema of schemas have the super nice and geeky and awesome property of being valid against itself. Yeah.
How?
Oh, then you just treat it as the instance and as the schema. You just open it twice as the instance and the schema. And if you ask, is it valid? The answer will be yes.
Okay.
Yeah. That's cool, actually. Very, very geeky. I think many people who use JSON schema do not go that far, or schema validation, but still it's interesting. Well, that's a deep conversation. Awesome. You deserve a break, right? That was a lot to digest. So let's take a break. I'll see you at 15 past 3. It's still on winter time there, so, no, on summer time. 15 past 3 for the continuation. Thank you.